So my name's Vaughan Langford. I work for SIFT Technologies and one of the principal scientists there. So today I talked about my exploration of SIFT-MS for odour analysis and how it compares with sensory analysis. So SIFT-MS differs from other techniques in terms of its speed of analysis, its ability to target all of those odour compounds that people sense, and also its high sensitivity. So it essentially mimics the human nose. So I think the outcome of my research is that SIFT-MS is really a complementary tool to existing technologies. The technologies being the sensory panel itself and also the gas chromatography, mass spectrometry, olfactometry approach. And SIFT-MS, because of its speed, its simplicity, really works alongside of those techniques. But having said that, it relies upon those techniques, and some of the data coming from them to date has not been sort of standard that we need to make the most of the fast analysis. So I think that's, for me, the next phase beyond today. An event like today's interest group meeting is outstanding in terms of seeing customers interacting with each other, learning from each other. I see there's cross-fertilisation of ideas even across scientific disciplines. So my experience of these events is that they are incredibly valuable. So, automated thermal desorption with SIFT-MS. So what I'm going to talk about is firstly how we've done it, how it's integrated, and then give 4 very brief case studies as to some potential applications. In terms of applications, it's quite new because, you know, we're just basically the product was announced at PitCon, the fruit of a year or more's collaboration between SIFT and Gerstel, and it hopefully within about 1 month it's available on the open market, so to speak. So why thermal desorption? Well, what we've seen with other automated analyses is that SIFT-MS provides greatly enhanced sample throughput. So Mark yesterday was talking about, you know, how fast you can resample sample bags. So the throughput is quite astounding with SIFT-MS. You know, then static headspace or something where you're incubating slows things down a bit. Multiple headspace extraction, Mark also talked about yesterday. You know, you repeat analysing, say 6 times per sample. So, you know, your throughput's dropping, but proportionally SIFT-MS is still far better than chromatography. So, thermal desorption as well. Why not? The other benefit of SIFT-MS compared to chromatography, of course, takes us back to one of the general benefits of SIFT-MS, and that is that with this system, because we're not using chromatography, we don't have the complication of, you know, one particular tube, one particular analysis type of column for a certain functionality of compound. This is a headspace example, but looking at automotive leathers in this case, where we can detect in one analysis, you know, your usual sort of VOCs and oxygenated VOCs, but also those tricky aldehydes that Mark loves so much, especially formaldehyde, the organic acids, the nitrogen-containing species, and here we've got trimethylamine as one example, and the sulfur-containing compounds such as hydrogen sulfide. So it's that combination really of speed and also diversity of compounds that means that SIFT-MS with thermal desorption may create a new paradigm. So, fully automated thermal desorption SIFT-MS. So just to go through some of those key points again. You know, we've got, with SIFT-MS, one of the differences, of course, and we saw this yesterday in Mark's presentation when he showed the schematic, is that with SIFT-MS we're analysing as we inject the sample. And I'll show you a modified schematic shortly. And this means that we can actually desorb and measure with SIFT-MS at the same time. And this is something quite new, so you can actually look at thermal extraction at higher temperatures in real time. You know, we've got the high sensitivity. What this can mean in practical terms is shorter loading times on the tube, less sample volume, you know, quicker from sampling to analysis. And also as I've mentioned, the ability to analyse a whole range of different compounds in one analysis. So what does it look like? That's it. And as I dubbed it last week at our meeting at Gerstal, this is basically the SIFT Technologies contribution, what I call the Black Beauty, which houses a cooled injection system from Gerstal, and above that is your standard TD 3.5 plus from Gerstal. In behind you can sort of see a little bit of the corner of some of the Gerstal flow control machinery, so to speak. Fairly simple sort of configuration. What's not shown here, of course, is the Gerstal MPS platform. And the point to note here is that the same system can actually analyse thermal desorption tubes and headspace with no change of inlet. So you can actually do headspace analysis as well and inject through basically what becomes a heated transfer line in that case. So a very, very flexible system, and also you can do bags if you have a bag hanger as well. So just to illustrate what I mentioned before, thermal desorption, GC-MS, you would desorb your tube, trap it onto the cooled injection system, and then do a very rapid heat, very rapid ramp to get a nice chromatographically resolved sharp peak. Then you've got your dead volume time, then you've got your sample elution and analysis. SIFT-MS, all we do is we desorb and we analyse synchronously. And then new LabSIFT software coming out which has an integration tool, part of it, which will integrate the curve and tell you the mass of analyte on the tube. So in terms of the software improvements or enhancements, one of the things, as well as doing thermal desorption with Gerstal, they have integrated into their Maestro software. There's a special new version of it when you're using it with a SIFT-MS instrument. That basically means for those who have the trigger interface, you can dispose of it if you're using the Maestro software. It means you've got a sequence table, so now there's seamless transfer of data between the two systems. And also, something that I've wanted to see for a long time is that it's pulling back and organising the data for you on the computer that you're controlling the instrument from. So it's got an auto copy and file feature. So that's at the Gerstal end. At the SIFT end, just quickly, we've got the option now to do batch analysis of headspace or TD samples is added. If you put in your sample flow and the split ratio for thermal desorption, not only will it tell you the mass on the tube, it will also tell you the concentration in the original sample. You've got flexibility about what you want to import from Maestro for your own table and reporting. Something that Mark's wanted for a long time, the ability to take that window and average it rather than just having a starting point and averaging to the end. So that's a benefit for headspace. That same window is used for integration if you're looking at thermal desorption tubes. So it can be either headspace or desorption analysis of your window. And related to that, the bits outside, there's some flexibility around what you can do with automated background subtraction as well. So that's enough of the background, the sales job. Let's have a look at some applications. So originally the inspiration for thermal desorption SIFT-MS came from the automobile industry. So a little bit of background on indoor air quality or vehicle interior air quality. Excuse me. A lot of this comes from East Asia, where there's a certain genetic disposition that means that some of the members of that population are much more affected and do not like those small volatile aldehydes that often come from human-made materials, in particular formaldehyde and acetaldehyde. And so what has happened in that part of the world is regulations around the emission levels into the car interiors. Some of us like new car smell. That part of the world particularly does not like it. So there's regulations that have been put in place. Now one of the challenges with the regulations is that it's a multi-instrument analysis. So you've got your aldehydes on your DNPH tubes, needs HPLC analysis afterwards. You've got a whole range of VOCs, GC-MS with thermal desorption tube GC-MS, and then also a total VOC, typically using an FID. So potentially SIFT-MS can address all of these things. So we had a gas standard made up. There's a bit of detail there about the ramp rate and so forth for the desorption, which we won't worry about because I didn't do the work, so it doesn't mean too much to me. But this is the sort of data that you can see coming out of your automated thermal desorption SIFT-MS instrument. As I said before, you're actually desorbing and measuring synchronously, so there's no trap and then inject. Desorption of the analyte and measurement in real time. Now what you'll notice here for 10x is that, for example, the formaldehyde is not a very significant signal, is it? So this is very, early work. There's more work to be done on suitable sorbents, but you do get a bit of formaldehyde signal and sensitivity even on a sorbent that's not designed all that well for it. Why the two humps and why the different shifts? Well, because we're desorbing in real time, we've got initially a little bit of the purge through the tube that typically you would do to remove some of the moisture. And those volatile aldehydes, you notice there's the light blue, the orange and the red. It's the volatile aldehydes that are coming off, those things that aren't retained well on 10x. Some of them, other than formaldehyde, they do have some binding sites that are a bit stronger, so you see a second hump. Whereas for the BTEX type compounds and styrene, it's just the one hump. They don't come off with that purge, then they come off and form a nice profile when you're actually heating and ramping the tube. And just some example data, recoveries in the table on the left, and for the same list of compounds, the breakthrough on the right. And you can see formaldehyde in particular, not so good on 10x, so there's a bit of work to be done there, but pretty pleasing early results for many of the compounds, especially for things, it's not bad for acetaldehyde and acrolein really from a tube that's not really designed for C1 to C3. And as well, you can actually look at desorption dynamics because of the real-time analysis. So in this case, basically purging for longer before you put your ramp on, and you can see that you've completely resolved the peaks. I guess in some sense you're doing a bit of chromatography on a packed column. But it's, there's all sorts of interesting things you can do when you can actually measure desorption in real time compared to just your trapped single shot sample at the end. Linearities with the concentration of the standard, very nice and linear with different loading, effectively different loading times, different loading amounts. Apart from our friend formaldehyde, it's still, but considering the breakthrough in that 0.95 is probably not too bad, but the rest of the compounds look very good. And just to have a look at some examples from real cars. So that's just 2 cars, 2 tubes done, just overlaid together with the LabSIFT software, and I've put the compound names down the side. And just to summarise, so what I've got on the left here, the red sort of shading is the sample window that we've got with that new integration tool, versus the integration, the little green, but it's a bit hard to see on this projector. But on the green, the window for the background subtraction is in green on the other side. And so, you're getting down to, very easily down to sub-nanogram quantities detected off those tubes with SIFT-MS. So, something different, some outdoor air analysis. Again, synchronous desorption and detection. Here we've just got some data for BTEX and styrene. Looking at the calibration curves effectively, or loading time is almost a calibration. Styrene's a little bit funny, but the other linearities look good. Lovely precision mark. It's precise technique. And some real data. So this is the low end of things. When you're at a petrol station, this is done for the American audience, so it's got gas station. It's done for a webinar. But you know, when cars are being refueled, these compounds come up a lot, but you know, just at more sort of standard sort of conditions. You know, looking again at very low microgram per metre cube concentrations with relatively short sampling times. We've started to look at breath analysis. So this is very, very early. It's this work that's going to be occurring over the next few weeks, doing some evaluation of the abilities with thermal desorption SIFT-MS for that market. 2 breath markers. These samples were collected into a bag, and then so someone breathed into a sample bag, and then the bag was sampled using a pump and a desorption tube onto a desorption tube. And just a couple of the very common markers, the acetone and the isoprene. So again, you can see that both of those compounds with 10X, you've got that kind of just the flow of gas through the tube is actually lifting some of the compound off, but we're collecting it quite well. And there's 2 different types of sorbent tube in this case. So we've purchased some biomonitoring tubes which supposedly are designed around breath-based thermal desorption analysis. And the very interesting thing about these results, if you compare them, is that, well, I mean, hydrogen sulfide doesn't trap well at all, which is probably not too surprising, very small reactive volatile. But ethyl mercaptan on the so-called bio tube actually it's got this very strange 3-hump profile, but it's also significantly lower even trapping of that sample on the tube from the same gas standard. So why that list of compounds? Well, isoprene is from person's breath, and then they've spiked in these other sulfur compounds from a gas standard which contains those 4 compounds. But it is interesting that this so-called biomonitoring tube may not be as good as maybe they think it is. And just to look at some data there, as I say, it's all very preliminary. So essentially the 4 bars on the left of each of these groups for each compound refers to blank and spikes in air, and then sampling with 2 different types of tubes. And the right-hand 4 refers to, instead of having air in the sample bag that the tube is being filled from, we have breath. So for isoprene, which comes from the subject, one of my colleagues, of course we have an isoprene signal on the right-hand side. But you can see again, you know, just very quick experiment, nice repeatability across those samples for the same tube for 10X. For, you know, the ethyl mercaptan is the one that really stands out and as not being so good for the biomonitoring tube. Finally, one other thing, and this is looking at thermal extraction of materials. So it's like thermal desorption, but here basically deliberately heating a material of some sort, polymer maybe, or cardboard, or we could do carpet, those sorts of things, and looking at the volatiles that are evolved as a function of temperature. So essentially similar sort of schematic as to what's happening, except instead of desorbing, we're now saying we're extracting and trapping. Okay, and I've still got to fix up that bottom slide, which should say sample extraction rather than sample desorption, but similar principle. Any questions on this? I refer to the polymer expert on my right, Mark Perkins. But basically a steady temperature ramp from time 0 and measuring continuously with SIFT-MS, and then reach 190 degrees Celsius and just hold. So that's just below the forming point for POM polymer. And there's 2 different types of polymer there, copolymer and homopolymer, and Mark again can tell you what the difference is. I don't know. But you know, very different temperature profiles for those different types of polymer. Something a little bit different, we quickly put together a demo for the PitCon show, and that involved something we were working on at the time. As you know from yesterday, I've been working on paper, so let's do some paper, thermally extracted. And you can see, you know, quite a different range of compounds now being extracted from the paper samples. Lots of those aldehydes again though. So special thanks to the people who have actually done the work and managed it. So from Gerstel, Dirk, Bremer, Eike, Kurt and Suzanne, and then my colleagues Deandre and Caleb. And just to summarise, so the ability of SIFT-MS here is this real-time analysis of, or fast analysis of a wide range of volatile compounds. So you can see that you can extract, for example, formaldehyde very easily and look at it in real time. The thing I forgot to mention was throughput. So for the atmospheric monitoring, you can have a throughput. For this case study we showed, they got basically the analysis time down to 3 minutes, 20 samples per hour for tubes. Typically it's sort of in that 12 to 20 tubes per hour of analysis. So very, very rapid, and as I said, applications are all new. That's what the team at SIFT is really excited about getting on to now that the system is integrated and working. And thank you.
Does anybody have any questions for Vaughan?
Or Mark.
I've got a question.
Uh-oh.
Thanks. So this is essentially you collect the sample offline, you can do whatever you want. So the connection from the thermal desorption to the SIFT injection port, and you said was just what's the temperature in there? When you can desorb whatever temperature.
Yeah, exactly. It's whatever you want it to be. That's a good question. About 200 degrees Celsius, I think, is a normal sort of transfer temperature.
Mark, I was asking you about it yesterday, because whatever you can get to the SIFT, you can analyze.
Yeah.
So this overcome the problem.
I think
you cannot bring to the SIFT
yeah,
before.
yeah. And of course, one of the things as well is that it's not just about thermal desorption tubes or direct extraction. There are other extraction approaches that you can use that are compatible with this, that we also want to try. Things like the thin film SPEME that Gerstel offers, which is basically SPEME coated on carbon fibre to extract perhaps less volatile things, or from a matrix that may be problematic for SIFT-MS. And also the twister type devices as well, those bigger capacity things, what do you call them?
Yeah, the SB.
Yeah, the stir bar things, but the twister in particular, they just pop inside, you dry them up, pop them in the tube, and you can directly thermal desorb them.
That's right, that exactly.
But you're correct, it is a hotter transfer path than is possible with the traditional approach. So
the stir bar is an interesting one, because, for example, if you're looking at a matrix that's, say, high ethanol, if you use a stir bar, the ethanol doesn't tend to absorb very strongly into the PDMS, and so it is a way of pulling out analytes using the sort of log KOW parameters to selectively pull out analytes and then stick it through the SIFT. So it does allow you to maybe analyse off of some more unusual matrices or high ethanol content matrices, for example.
Well, I think more importantly too, it's the semi-volatile.
yeah, and that's what we're interested in too.
With the direct.
Yeah, and we've seen some, I was at a presentation last year where someone was using the thin film SPEME in water for pesticides and that sort of thing, and I sort of thought, wow, this may make it possible. It's not the sort of thing you're going to see in air, but if you can extract them, reduce the amount of water that's there a bit, and away you go.
You're going to have to increase the mass range of the detector, aren't you?
Well, it goes up to 400. Most pesticides I think are less than that.
One thing on your presentation I saw particularly noticeable with the BTEX compounds was the peak maximums were slightly different,
Yes.
and seemed to follow what you would expect for the volatilities of these compounds. As you said, chromatography.
Yeah, it
Any
is.
other applications you can think of that this would be useful, where you can ramp
Well,
the temperature
I
of the
think
TD tube and potentially force a small amount of chromatography between?
Well, this is the thing. There was a paper that we've not from Eastern Europe using SIFT-MS with a home-built thermal desorber, but the reason we haven't promoted it was that they were doing very slow chromatography off their homemade desorption tubes. By very slow, I mean 30 minutes they were desorbing into a supposedly real-time analyzer. there's possibility, you know, things like the monoterpenes that are not easily resolved, that you can, you know, you could look at integrating under curves and things like that and peak fitting. So, you know, in a sense it does provide, you know, a little bit of some flexibility, you know, there's lots to be done, so just think about joining the revolution.
Is this easily added onto an existing SIFT?
Yes. The main, you need, I mean, the hardware, of course, and that special inlet.
So what you saw in the lab yesterday with the injectable inlet, what you do, if you get that, you would just replace it with the TD inlet. And as Vaughan says, if you load up the thermal desorber with a blank tube with an adapter on the top with a septum in it, then the TD then acts essentially as a sort of hot transfer line, and then you could do headspace injections through the top of the TDU instead. So you wouldn't need to change out for headspace or TD. Once you put the TD inlet on, you actually have a headspace injector as well, and then we do everything we did, as you saw yesterday, with the stuff I showed yesterday. So it would be a fully injectable inlet on top of the system that you would leave there, and it would, it's simply just replace a few screws, in it goes, and job done.
But also from bags as well. You know, if you have the bag hanger, it's essentially a headspace experiment, you know, injecting with the needle through that same setup. So it's all one platform. You can have, you know, you can cycle between them on any given day with no hardware changes, and I think the tool will change, you know, change the liner for you and everything.
I think that's an interesting point actually about the fact that if you were doing headspace in a blank TD tube, the TD tube is acting as a liner. If you've got carryover issues, switch the liner out and put a new one in. So it starts to act like a transfer line in a standard system actually. I hadn't thought of that. That's a good point, that you could potentially start contaminating up your liner, because it's just operating on a TD system. The instrument can just change the TD tube out, so it's an automatic liner exchange on a headspace instrument now as well. So you can deal with contamination issues. You clog your system up with, for example, glycerol, for example, and you just switch the liner out and get some decent results off of a clean liner actually.
So lots of automated possibilities.
Actually, that might give your colleagues in SIFT, because in your library you don't have any compounds with relatively higher boilers, right? Because you couldn't get in before. Now could you actually demonstrate, for example, use the thermal desorption, get some of those compounds, show the range of, really expanded range of your compounds?
It's a good point, a very good point. You send us some.
And the process of getting the data into the library is actually relatively straightforward if you have access to the compounds. So if you know the loading on your tube, if you're interested in a compound that isn't in the library, and you could load it up onto the tube, you know your tube loadings, run it through the system, and you can just switch some equations around and get reaction rates off of it, and actually put the library entry in quite straightforward.
No, you're right, but before, without thermal desorption, you could not.
No, you couldn't do that. No, exactly.
You have it with the
How does that work though with the fact that it's not coming off at one time? So
the integration tool gives you the total mass on the system.
Yeah, I guess the rate just averages it, we average over it.
Yeah. I don't know, I haven't got one in the lab yet. I'll tell you.
Yeah, when we get one.
Okay.
Thank you, Vaughan.
Okay.